the last of our circle geometry theorems. It's actually 3 theorems, but personally I think they're all the same theorem. Let me show you the one I'm talking about. It's our product of intercepts. So if you draw 2 chords in a circle, obviously they're going to intersect unless they're parallel. So providing they're not parallel, what we're talking about is this little theorem, that AX times BX will equal CX times DX. And that's what we call the product of the intercepts of intersecting chords in this case. The way I tend to think about this theorem is like so. The endpoint of the chord to the point of intersection times the endpoint of the chord to the point of intersection is equal to the endpoint of the chord to the point of intersection times the endpoint of the chord to the point of intersection. Alright, so let's just have a look. So you got chord AB. The endpoint of the chord A to the point of the intersection, X. Endpoint of the chord B to the point of intersection, X. So on that chord, AX times BX. And that's going to be the same with the other chord, endpoint of the chord C to the point of intersection X times endpoint of the chord D to the point of intersection X. But thinking about it that way means now when I have this situation where instead of intersecting chords we have intersecting secants, it's still exactly the same idea. Because it will still be the endpoint of the chord, not the endpoint of the secant, the endpoint of the chord. So when you draw a secant, you actually create a chord in that secant. So the endpoint of the chord, A, to the point of intersection, which is all the way out here at X, times endpoint of the chord B to the point of intersection X, and then you go to the other secant, is equal to the endpoint of the chord D to the point of intersection X times endpoint of the chord C to the point of intersection X. So 2 different theorems, but actually they're exactly the same. The difference in the reasoning is instead of saying intersecting chords, we say intersecting secants. Then there's a third one. Where you've got a secant, but the other one is a tangent. Now, to do this one, we have to imagine the chord with the tangent is actually the single point A. So it's a chord, if you like, of 0 length. It's just the point A. Because then it works. Because the endpoint of the chord A to the point of intersection X times the endpoint of the chord A to the point of intersection X, so AX times AX, in other words, AX squared. And then you look at the secant, endpoint of the chord D to the point of intersection X times endpoint of the chord C to the point of intersection X. And so you get CX times DX. This one is the square of the tangent. I wonder why I said tangent's plural there. Really, I suppose it's singular. There's only one tangent. But anyway, square of the tangent is equal to the product of the intercepts. So, well, that's incredibly generous for 3 periods, isn't it? 1 A, 2, 4, 6, 9 A. But anyway, it does see the end of our circle geometry theory.